SwayamPrabha. Digital India. Educated India.
So, hello everyone. So, welcome to the second lecture, and we are going to learn today the concept of traction vector and stress tensor. Okay. So, this is lecture 2. So, in your first lecture we have learnt about vectors, tensors, how to work with tensors. So, you should really revise that lecture before proceeding here. Okay. So, let us see, begin with the traction vector. So, suppose that we have a arbitrary body all right, which is clamped at one part of the boundary. So, you see this dashed line is used to denote clamping, which means that that part of the boundary cannot move, all right, it is fixed. And suppose somewhere else you are applying force, all right. So, this is an arbitrary body which could be the desk on which your copies are there, the table, your own hand, leg, anything, or any machine part, all right. So, when you apply the force, the body is going to get deformed, right, and as the clamped part is not supposed to move. So, that remains where it was, but the remaining part will go down, is not it. Let us say it becomes something like this. So, clamped part is where it was, but the remaining part goes down, and you have the force present here. So, you see in this deformed configuration, when the body is deformed, the body is, we say that the body is under some kind of stress. No, it is not relaxed, because there is force acting on the body. So, at different points in the body you have some kind of stress, which we will define what it is. So, if you, for example, take a section of the body, divide the body into two parts by taking a section. So, suppose I draw this section, okay, and it is an internal section. So, you cannot see this section, that is why it is a dashed line, all right. So, this section divides the body into two parts, part A and part B. Okay. Let us focus on part A. So, if I just draw part A, again it is difficult to draw it accurately, but suppose this is part A and here is that section, all right. So, on this section, which was an internal section of the whole body, part B is going to exert some force on part A, and that force would be distributed through the section. So, that force could be something like this. So, when the arrow is going away from the body, that means the body is being pulled and at some places it could be that the body is being pushed. So, part B, on the top part it is pulling and on the bottom part it is pushing. Okay. So, on this section at different points you will have different kind of nature, pushing and or pulling nature, all right. And then the question comes, what is the intensity of the force with which part B is pulling the part A. So, the motivation is what is the intensity of force with which part B is applying force on part A. Okay. So, that is the question. Now, you see when you try to answer this, you come back to this section, this internal section, and you notice that at different points in this section, so at different points in this section, the section that you see here, so at different points in this section the intensity of the force would be different. So, how to get that intensity? So, this intensity means force per unit area. Okay. So, let us try to redraw that section. So, I am going to draw part A again. And here is the section, and suppose I want to know the intensity at some point which I call as x. Okay. So, this point is a point x. Remember that when I write this x with a tilde below, it is a vector. One tilde means it is a vector, two tildes means it is a tensor, second order tensor. Okay. Why do not we draw small circle about that point? You see that point is, or this circle has to lie on this plane, and this plane may have some normal n. So, n is the direction of the normal, x is the point where I want to know the intensity. Okay. Area enclosed by circle, that is delta A, all right. And also suppose that on this circular disc, you have force acting from the other part of the body. So, total force suppose it is equal to delta F, all right. Let us take the limit delta A going to 0, delta F by delta A, all right. So, while taking the limit I will write it here, while shrinking the area of the circle, the circle must always contain the point x where you want to measure the intensity. Okay, so, what do you think? What is this limit going to give us? You see, as you shrink the area of the circle, the force applied by part B on that area is also going to decrease, is not it? Because total force is what? It is the sum of all the forces that acts on this area. So, as you shrink the area of the circle, the force delta F also decreases, but in the limit it is going to attain a value, all right, and that value is called traction. Okay. So, I am going to denote traction by, so traction which I will denote by the vector t, again with a tilde because it is a vector, and then I have to say at which point I am measuring the traction, like here at which point I am measuring the intensity, that is the point x. So, traction at point x, so it depends on what point, and it also depends on what plane. So, the normal to the plane n. Okay. So, it is a function of two variables x and n, and this is now equal to limit delta A going to 0 of delta F by delta A. As we went through this definition, I think the physical definition is clear. Traction is basically telling us what is the intensity of the force with which one part of the body is exerting force on the other part and at a given point x. Okay. And you see, by definition it is force divided by area. So, it has the unit of pressure. So, it has the unit of pressure, but it is not exactly pressure. We will let you know how traction is different from pressure. So, think of your body, any arbitrary body. So, it has got several points in it, right. So, this body is under some force like it was earlier, and think of a point x here, another point y here, another point z. So, there are 3 points, there are actually many points. So, at each of the points you will have different traction, because you see by definition traction is a function of x. Not only this, just at a point itself, let us say at the point x, at a point x itself you can think of several planes. One plane could be this, which has the normal n 1, okay, normal 1. Then you can have another plane at the same point whose normal is n 2. Okay. So, traction, as I said, it varies from point to point, but even at a point traction on two different planes are different. So, on plane with normal n 1 traction will be something, and on plane with normal n 2 traction will be something else. Okay. Let me give you a very simple example to make it more clear. Think of a beam. Suppose it is a rectangular beam. Okay, so, that is a rectangular beam which is clamped at one end, and on the other end you are applying some force P, and suppose that the cross section area here is A, all right. So, the cross sectional area I will write here is equal to A. Now, let me think of a section, this particular section, okay, this blue section has got its normal along the axis of the beam, and let us call this E1. And what do you think, what is the traction on this plane? So, you have to find out what is the total force that is acting on this plane and divide by the area, right. So, the traction here T on this plane whose normal is E1. So, I will write it with a superscript 1. So, superscript 1 means its normal is E1. So, this T1 is simply PE1 divided by area. So, that is P by A E1. Supposing that the traction is the same at every point on this section, which is not the usual case, but let us suppose in this case at every point of this section you have the same traction, then traction is simply the total force divided by the area, just P by A E1. Okay. Now, let us take a different section. Okay. So, suppose I take a different section whose normal is somewhat tilted, all right. So, that is the normal which I denote by E1 hat, and suppose the normal makes an angle theta from the axis. Okay. So, I will write here that E1 hat makes an angle theta from the axis, which in this case is E1. Now, what do you think, what is the area of this section which is tilted? Definitely that area has to be bigger than the cross sectional area A, is not it? And if you work it out carefully, you will see that the area which I denote by A hat is actually A upon cos theta. So, then what is the traction T1 hat? So, that is going to be equal to total force, which is P E1 divided by the area, which in this case is A upon cos theta, A upon cos theta. So, this becomes P cos theta by A into E1, all right. So, you can see here the tractions on two different planes are different. So, I am just going to write that thing, it is a very important point. Traction not only varies from point to point in the body, but even at a given point traction on different planes are different. Okay. Now, how many planes can you think at a given point? Draw that figure again, the body, and I am at a point x. How many planes can you think of which is going to pass through the point x? It is a infinite. You see, this is one plane with normal n1, another plane with normal n2, you can keep on going on. So, the bottom line, there are infinite planes at a point. Well, that means you have to know, if you want to know traction, even at one point, you actually need to know traction on all the planes at that point. How can you store the information of all the planes, which is infinite in number? First of all, why traction is important? See, it is important because it tells us by definition what is the intensity of force with which one part of the body is pulling or pushing the other part of the body, right. So, it kind of tells you what is that intensity. If that intensity is a lot, then the body can actually fracture, isn't it? So, that is why traction is important. If the value of traction is lower than some threshold value, then the body is not going to fracture or it is not going to fail, but if it is more than the threshold value, then it can fail. So, that is why traction is important. Now, at a given point also, since traction varies from one plane to the other, that tells us that if, let us say, on one plane traction has got lot of value, but on some other plane it has got smaller value, then the probability of failure is higher on the plane on which traction has got larger value. Okay. So, that is why traction is important. So, I am going to write it here. Okay, that is really a very important information, but the problem is there are infinite planes at a point. So, how to store the value of infinite planes? See, the point itself is infinite, then at a given point the planes are also infinite. So, it is infinite into infinite. How to store all such data? Luckily, there is a very nice theorem. If we know traction on 3 independent planes, we can then find the value of traction on any other plane. So, what does this mean? That means just store the value of 3 planes and then use the formula to get the value of traction on any other plane. So, that is really a very useful theorem. Let us work out that theorem. Okay. So, we are going to draw a tetrahedron. This is again my body, and think of this point x, and suppose I know the value of traction on 3 different planes at the point x, and then I want to know what is the value of traction on any other plane. Okay. So, we have to draw a tetrahedron whose vertex will be at x. So, this is the tetrahedron. Okay. The vertex is at x. Let me redraw the point x. So, this point is x, the vertex of the tetrahedron. So, you see this tetrahedron has got 4 planes. Can you see the 4 planes? Let us zoom this diagram. So, I am going to draw a bigger tetrahedron. Okay. And here is your point x, the vertex. So, now I guess you can see the 4 faces. Maybe we can, if we level it, it is more clear. Let us say this is O, then A, then B, and this is C. So, we have 4 faces, O, A, B, that is the bottom face, it is the bottom. Then we have O, B, C, then we have O, A, C, and we also have A, B, C, the 4 faces. Or let me put a coordinate system here, so that OA, along OA we have E1, along OB we have E2, and along OC we have E3. Okay. So, the plane OAB, what is the normal to plane OAB? It is minus E3, we have to always look at the outward normal. Okay. So, this is the tetrahedron and I want to look at the outward normal of all the 4 planes. So, here is the plane and then the normal. So, OAB has got minus E3, right. OBC, what is the normal to OBC? That is minus E1. What is the normal to OAC? That is minus E2. And what about ABC? Okay, that is a tilted plane. So, let us say its normal is n. So, what I want to do is I will say that we know the tractions on the 3 planes minus E1, minus E2 and minus E3, and then I want to know what is the traction on the tilted plane. Okay. So, to do that, let us apply Newton's second law to the tetrahedron. Which tells us that net external force on any body, which in this case is the tetrahedron, net external force on any body has to be equal to rate of change of linear momentum of that body. Very simple Newton's second law, where P is the momentum. Okay. So, what are the external forces that acts on this tetrahedron? See, we have to imagine taking out this tetrahedron from the original body. So, when you take it out, the other part of the body is going to exert force on the tetrahedron. And since you have 4 faces of the tetrahedron, the other part of the body is going to exert traction on those 4 faces. Okay. So, what are the tractions that acts on those 4 planes? So, on OAB for example, the traction that acts is T minus 3, okay, T with a superscript minus 3, because the normal is minus E3. So, this external force, it has got 2 components. One is the contact force. There are 2 kinds of forces that acts on this tetrahedron. One is the contact force, which in this case is the force applied by the other part of the body due to it being in contact with the tetrahedron, and due to contact we have this traction forces. So, I will write here contact force means the traction force. And then we have other force also, which is non contact force. Can you think of what could be a non contact force? So, this is the force which is getting exerted on this tetrahedron from some other agent without that agent being in contact with the tetrahedron. Okay. Can you guess one of such forces? For example, the gravity force, gravitational force that is being applied by your earth, okay, by the earth. So, one example is of course, the gravitational force. And this is also denoted as body force, okay, body force. Body force because it acts on every point of the body, every point of the tetrahedron. See, the gravitational force, for example, is it's particle to particle or from earth to every point of the tetrahedron, and body force has got the unit of force per unit volume. Okay. So, the body force, because it acts on the volume of the body. So, body force, the unit of the body force, its unit is force per unit volume, whereas this contact force, it acts on the surface of the body, right, the four surfaces of the tetrahedron. So, the unit of the contact force is force per unit area, just like the traction force, it is force per unit area, right. And if you want to get the total force due to the contact force, you have to integrate over the area on which it is acting. If you want to get the total body force, then you multiply the body force that is acting with the volume of the body to get the total body force. Okay. So, there are two kinds of external forces that acts on the tetrahedron. The body force, what is that? That is the weight of the body itself, right, mass times the g, the acceleration due to gravity. So, what will be force per unit volume? If you divide by the volume, it is density times the gravitational acceleration g. So, body force, if it is gravitational, it is simply rho times g, where g is the acceleration due to gravity. So, g is acceleration due to gravity and rho is the density. And for the contact force, here we have the traction. So, there are T minus 1 which acts on the minus E1 plane, then we have T minus 2, we have T minus 3 and we have T n, the 4 traction forces. Let us find out the total force due to these two kinds of forces. You see, T minus 1, it is acting on minus E1 plane of the tetrahedron, which in this case is the plane OBC. Okay. So, suppose the area of that face, the area of the face OBC here, suppose that is A1, because its normal is minus E1, I will say its area is A1. So, what is the total force due to traction T minus 1? Assuming that the traction is the same on that face, you simply multiply traction with the area, is not it. So, the force, total force, so I am going to write now F external T minus 1 into A1, where A1 is the area of the face OBC. Then we have T minus 2 into A2 plus T minus 3 into A3 plus T n, see T n is the another traction, into A n, let us say A n is the area of the that tilted plane with normal n. So, this is the total contact force. So, I am going to write here, this is the contact force plus the force due to the body force. So, that has to be rho g multiplied by the volume of the tetrahedron, is not it. So, that is going to be volume V. So, I will write here, that is the volume of the tetrahedron, right, and this has to be equal to, from Newton's second law, this is equal to rate of change of linear momentum of the tetrahedron. And if you remember your first year mechanics, you could also write it as mass times acceleration of the center of mass of the tetrahedron. Okay. So, what is the mass of the tetrahedron? That is rho, the density, times the volume, that is the mass. So, it is rho v, that is the mass, times the acceleration of the center of mass of the tetrahedron. Okay. So, we have got this equation based on Newton's second law. Now, we have to do some trick. Can we write down volume in terms of the area, for example? You know, if you look at this tetrahedron again, so suppose H is the perpendicular distance of ABC from vertex So, if that is your H and the area of the tilted plane is A n. So, the volume V is then 1 by 3 into A n into H. Okay. You can also relate the areas A 1, A 2, A 3 in terms of A n. See, if you project the area A n, the tilted area, if you project along the direction E 1, that area is nothing but O B C, which is A 1. So, A 1 is the projection of A n along E 1. Similarly, A 2 is the projection of A n along E 2. Okay. So, I am going to write them here. So, A I, where I goes from 1 to 3. So, A I is the projection of area A n along E I, and then with some geometry you can then prove that A I is then nothing but A n times the normal n dot E I. Okay, this is the dot product. So, the direction cosine of the normal n, n dot E I. So, you multiply with that direction cosine and you get A I. All right. So, it comes from geometry, and then we have also found out that the volume V was 1/3 A n times h. So, let us plug in these formulas in our equation and see what we get. So, each of the areas A I is A n times n dot E I. So, A n is common. So, A n comes out. So, we have A n times t minus 1 n dot E 1 plus t minus 2 n dot E 2 plus t minus 3 n dot E 3 plus T n plus rho g into volume. So, that is rho g times the volume, that is 1/3 into A n times h, and this is equal to the right hand side rho v A center of mass, rho again volume 1/3 A n times h into acceleration of the center of mass. All right, very good. So, we have this formula with us, and you can see A n is common everywhere. So, we can divide by A n. So, we can cross A n everywhere, and let us try to now rewrite this formula. So, this means T n plus summation over I equal to 1 to 3 T minus I n dot E I. So, the three terms have been written together using summation plus rho h by 3 into g minus acceleration of the center of mass, and that is equal to 0. Okay. So, we found this formula for the tetrahedron. We are not done yet, just small step remaining. See, what was our goal? We wanted to write down the traction on the plane n in terms of the other three tractions. So, we are basically trying to write down traction on any plane in terms of three other planes at a given point. All the planes have to pass through the same point. Now, you see, in this case with the tetrahedron, plane 1, plane 2, plane 3, all three of them pass through point O, but the plane n, the tilted plane, is not passing through the point O, right, whereas our goal is to relate the tractions on all the planes which pass through the same point. So, what we can do now is to shrink this tetrahedron. So, why do not we shrink this tetrahedron? And the way we do it is by taking this h, this perpendicular distance h, let this h go to 0. So, as h goes to 0, this tetrahedron is going to shrink to the point x, is not it? And then all the planes will then pass through the point x. So, that is a very nice strategy. So, shrink the height h to 0. So, that is what I am going to do now. Come back to the formula that we derived here, and in this formula I am going to apply limit h going to 0. And what is this physically doing? So, physically this is shrinking the tetrahedron to the point x. Okay. So, can you now see what is going to happen as you take the limit h going to 0 on this, in this box inside you have got this term proportional to h. Can you see this term that you see here, that is proportional to h. So, in the limit this is going to vanish, is not it? So, in the limit this becomes 0. So, that is really very interesting. So, I am going to write it in the limit h going to 0, the terms corresponding to body force and acceleration drop out, and finally, what remains is a very nice formula that T n is equal to minus summation of I equal to 1 to 3 T minus I n dot E I. Okay, there is this last step remaining here. See, what can you say about T minus I and T I? So, the question, what is the relation between T minus I and T I? See, by definition T minus I is the traction on minus E I plane. For I equal to 1, T minus 1 is the traction on minus E 1 plane, whereas T 1 is the traction on E 1 plane. So, you see it is the same plane, but with two different normals. So, if I redraw our body and think of this internal section, I get two parts, and the sections have normals exactly opposite. And what can you say about the tractions on these planes? They will also be equal and opposite due to the Newton's third law, is not it, because they are action reaction pair. So, I am going to write it, they are action reaction pair. Which means T minus I is equal to minus of T I. So, if you finally put this formula up there, so now you got the final result that you wanted. So, the final result is traction on a plane n is the summation of I equal to 1 to 3 T I n dot E I, that is it. So, we have derived a very important formula, traction on any plane n. If you know traction on 3 planes, you simply apply this formula and you get traction on plane n. Okay. So, I am going to stop here, and we will continue in the next class, where we will learn about stress tensor. You know, this was all about traction, but in the next class we are going to learn about stress. Okay. So, I hope you enjoyed it. Thank you.